Evening, everyone.
Hello.
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 Everybody always sounds so excited. Hello. Oh God, it's stats again. I get it.
It's 7 o'clock and it's been a long day.
Exactly. It's a whole group of Eeyores. I totally feel your pain. All right, let's see. Okay. Who wants to start us off?
I will.
Yep.
I need help with okay, I have like two questions, but we can start with 4.86.
4.86.
Yes, let me see which 4.86. I use the CDF formula for probability, the XMS for that first part of the question. Was that correct?
You're talking about for part A?
Honestly, I'm confused on all of this. Like, I get a headache even just looking at the final project because I don't even know.
Well, so we're doing normal CDFs for everything. The only thing you have to worry about is a normal CDF always gives you probability to the left of your measurement. So if the question is asking for the probability of something being less than a certain measurement, then the CDF will give you that answer. However, if it asks for the probability of something being greater than a certain measurement, then you have to run the CDF and subtract it from 1, because the CDF will give you the stuff below, and greater than is asking for the stuff above. And then, of course, if it asks for the probability of being in between two things, then you have to run the CDF on both of them and take the difference, because, again, the CDF does less than. So the in between is going to be less than the upper one, but greater than the bottom one. So that's why you have to subtract the bottom one from it. We talked about that last time, but basically we're always doing CDF. So if you're trying to do question 86 part A, yes, you're going to do a normal CDF, and you just have to kind of use the context of the question to determine, what you're looking for, what it means, right? They tell you that if their blood pressure exceeds, i.e. is greater than 150, then they're considered to have high blood pressure, and then they prescribe medication. And they go on to say that there's a problem that, blood pressure varies during the day. So, if you just measure it once, you're not really getting an accurate picture of that patient's blood pressure. So part A gets to that idea. They're saying, okay, so if we know that blood pressure readings, right, systolic readings is just blood pressure. If we know that readings during a given day have a normal distribution with a mean of 160 and a standard deviation of 20. So that means if you were to check your blood pressure over and over and over again, like every minute during the day, and had, hundreds of readings, you would see that those readings, if you plotted them all out on a graph, they would create a normal curve, meaning, you created little bars or little lines to represent how many readings you had, how many times you got a reading of 150, and how many times you got a reading of 151, and how many times you got a reading of 170 and 160, and so on and so forth. And then you plotted all those little bars, made your own little frequency, bar graph. It would have a nice, pretty little perfect normal distribution. And the mean of those readings would be 160, and the standard deviation would be 20. So with that given information, the question is, okay, so now we know that if we ran this experiment, a million times, we check somebody's blood pressure over and over and over and over again, we would get this set of data where we would have, certain numbers of each data value, right? Each data value would have a certain frequency, but it would be in such a way that if we plotted it all out, it would have this nice little pretty normal bell curve shape. Given that, if we now go and just randomly pick one piece of data out of this big set, of 1 million measurements, that's the same mental concept, right? It's the same theory as if we just went and measured their blood pressure once, right? Because measuring their blood pressure once, in theory, is the same thing as just picking one measurement out of a hat, when that hat contains, 1 million measurements that have this normal distribution attribution. And when you have a normal distribution, all that means is you've got more measurements in the middle than you do have out at the end. Because remember, the normal curve, is a bell curve. So you have the vast majority of your stuff clustered in the middle. In fact, if you remember what the empirical rule says, that we have 68% of our data within just one standard deviation, right? We've got this nice, pretty bell curve, and the mean is always in the middle, right? This is always the average, the mean, the mu. And we can see that we have a lot more stuff here than we do in that same distance, right? So if this distance is one standard deviation, right? And then we take that same distance again, this stuff out here is less than this, right? And as we go further and further out, we get less and less stuff because it's shorter, right? So there's less area. So the idea is, if I now just, it's like throwing a dart at a dartboard. If I just randomly pick one piece of data out of that hat, I'm far more likely to get a result in this middle range than I am to get a result way out here, because there's just more data in that middle range than there is out there, right? And so that's how we can then attribute probabilities to everything. We can say, okay, we can now calculate the area under this normal curve, and we can tell you the likelihood of one random choice falling, anywhere on this curve. And so this particular question says, what's the probability that a single measurement will fail to detect that a patient has high blood pressure? Okay, well, that is just a fancy way of saying, what is the probability that that one measurement will be 150 or less, right? Because they tell us up here that your blood pressure has to be above 150 in order to be considered high blood pressure. So when they say, what's the probability that one measurement will fail to detect that the patient has high blood pressure, just means that that one measurement is 150 or below. So that's really just a fancy way of saying, what's the probability that X is less than or equal to 150, which, remember, because this is a continuous, is the exact same thing as just the probability that X is strictly less than 150. Doesn't really matter either way you think about it. We just now know that the X that we're going to use in our computations is going to be 150, because that's the cutoff. That's what we're caring about. And because it's a less than, again, draw pictures, guys, so that you can figure out what the hell they're asking. Here's my 150, and we're looking for everything below it, because we're looking for less than or equal to 150. And that's good, because that's what a PDF gives us, right? Any PDF, whether it's a binomial PDF, a normal PDF, CDF, that's what a CDF gives us, whether it's a normal CDF, a binomial CDF, there's ANOVAs, all these different, the F distributions, all these things. If you calculate a CDF on them, it will always be the cumulative distribution function, which means it always goes that number and less, right? So that number and below, that number and to the left, however you want to think of it, they all mean the same thing, but it's just that stuff and less than it. And so for this question, because we want everything less than 150, we can
Dr. McBride,
yeah.
doesn't that say exceeds 150?
Well, they say if it exceeds 150, they have high blood pressure. The
Okay.
question says, what's the probability that you take a measurement and it fails to detect that they have high blood pressure,
Oh, okay, okay.
right? Do you see that?
Yeah, I see it now.
So that's why it would have to be less than 150, because if it was greater than 150, that would come back and go, oh crap, I've got high blood pressure. But if it's less than 150, it fails, right, to detect high blood pressure.
Okay, okay.
So we're going to
Miss-
go over here to our normal CDF. The X that we care about is 150. The average that we have is 160. And the standard deviation that we have is 20. And we just run that. And that's our answer. Right? A little bit more than 30, almost 31%. So that tells us that if you just check a patient's blood pressure once during the day, there's a 30, almost 31% chance that you're going to fail to detect that that patient actually has high blood pressure, because there's a 31% chance that you're just going to get a reading that's under 150, even if the average is 160. You know, if someone has an average blood pressure of 160, then they have high blood pressure, because we've been told that 150 is the cutoff, right? So the reason why the average of this distribution is 160 and the standard deviation is 20 is because we've made this up, but it's the fictional context of this patient has an average blood pressure of 160. And a standard deviation of 20 just means that during the day, their blood pressure is going to vary greatly. And it does, right? Our blood pressure goes up and down all day, depending on stress level, exercise level. If we've just eaten, there's all sorts of things that can screw with your blood pressure that can make it fluctuate during the day. But you will have an average over the day, and that average is technically what your blood pressure is, right? And so this scenario says that this patient has an average of 160 and a standard deviation of 20. So ergo, this patient has high blood pressure because it's over 150. But if we only tested it once during the day, there's a 31% chance of getting a reading less than 150, and thus us going, oh, your blood pressure is fine, even though in reality, they have high blood pressure. Now, not extremely high. I mean, it's only 160 instead of 150, but still, the whole point of this question is twofold. One, so you learn basically a little bit about stats and how to, figure these things out. But two, to see that a single measurement is not always accurate, regardless of the context. This happens to be blood pressure, but, in any case, just one measurement can be misleading. And this leads us later in statistics to talk about confidence intervals and alpha levels and all those kinds of things. But that's what's happening here, right? So then the second question is, okay, what if we take 5 measurements during the day? What's the probability that the average of those 5 measurements will be less than 150? Well, wouldn't you think that because the average of all the measurements is 160, that the more random measurements we take, the closer that average should get to 160, right? So if we take 5 measurements, the likelihood of all of that average still being less than 150 should be substantially less. And it is, because the central limit theorem tells us that as you take more measurements, they cluster together more. And when they cluster together, right, when they squeeze together, the standard deviation gets smaller. And when the standard deviation gets smaller, the chances of you being further away from the mean also gets smaller, right? Because as everything squeezes together and your curve all of a sudden looks like this, and you're still on the same scale, right, where this is 160, and 150 is still this far away. Well, now look at how much area is left of 150, right? It's far less likely to get a measurement less than 150 than it is on something that's all spread out, like this example up here. And that's what happens when you take more and more measurements. And the central limit theorem tells us that there's an actual very direct relationship between how many measurements you take and the effect that it has on the standard deviation. And that is that you literally just take the original standard deviation and divide by the square root of your sample size. So if you come along and take 5 measurements instead of 1, you're now going to take that 20 standard deviation and divide it by the square root of 5. So if we go back to our code, and instead of having a standard deviation of 20, we divide that by the square root of 5 and run this code. Instead of being 31%, you know, that it could be less than 150, look what happens. It's only 13%. And the more measurements you take, the more accurate it's going to get, right? The more closely that average of those measurements is always going to get closer and closer to the true average of you can think of it as the population that you're sampling from. And so the likelihood of getting something that deviates from that mean of 160 is going to get smaller and smaller and smaller.
Can you show us how you put the square root in? I wasn't seeing that on your screen. And I keep getting an error. I don't know what I'm doing wrong.
So all you have to do is type in SQRT parenthesis 5 close parenthesis after the 20. Right?
I didn't close the parenthesis. That's why. Thank you.
Yep. All right. What else? What's next?
On part C, with the formula for that we would use, would it be the probability of 150 minus K is less than Y, and Y is less than 150 plus K equals 0.01?
Close. You're thinking of if you were asking that an interval around 150 was 1%, right? So what you were saying is visually, if you had a distribution, right, and here's the 150, and you went plus and minus K in both directions, that would have to be a total of 1%. That's not what they're asking for. They're saying basically how big does your sample have to get so that this curve gets narrower and narrower and narrower, so that when you run the analysis, this area is 1%. Because they're still saying how many measurements would be required so that the probability of failing to detect a high blood pressure is at most 1%, meaning, you know, failing to detect means that the average of all of your measurements is still less than 150. So it's still the exact same question. We're still looking for the probability of getting measurements less than 150. We're still looking for the probability of the average of all of those measurements to be less than 150. Only now we're asking it in a reverse order. Instead of, hey, if you take 5 measurements, what's the likelihood of being 150? Or if you take 10 measurements, what's the likelihood of being less than 150? We're asking, hey, how many measurements do you have to take in order for that likelihood of being less than 150 to be 1% or less? And that's when you have to run the quantile question, the quantile formula, because the quantile formula does the exact same thing as the CDF. It just does it Jeopardy style, right? It does it in reverse. It gives you the question instead of the answer, right? So instead of you going, hey, if my sample size is this, what's my probability? It says, hey, if my probability is this, what sample size do I have to have, right? So it's the same question, but in the opposite order. So all you have to do is go, all right, I want my probability to be 1%. And my mean is 160. And my original standard deviation is 20. And so what sample size do I need to make this happen? Tells me 113,473. Well, that doesn't seem right, does it? Because this is taking into account, it's not taking into account the central limit theorem, right? So this is a multi-step process in order to, because we don't have the ability to change this with the quantile function. That's the problem with the quantile function is we can't say, hey, our standard deviation is going to be 20 divided by the square root of n. Now you figure out what n is, right? It can't do that. What you have to do is you have to work with those dreaded z-scores that we talked about. So let's get a bigger blank screen here so we can visualize what we're talking about. So here's my mean of 160, right? And with my normal curve, I do 150 and I get all this area. And the first thing we did, I think it was close to 31%, right? It was right around 31%. And then our sample size gets bigger, right? And with a bigger sample size, the curve gets, oh gosh darn it, why does it keep doing this to me? So as we get our bigger sample size, we get a thinner, taller distribution. So remember, this is still sitting on the number line, right? So the distance from 160 to 150, still the exact same distance because we're still sitting on the same number line. All that's happened is our original curve, that looked like this, right? You've got a lot more area underneath that curve than you do now under this one, because the curve has been, it's almost like you've squeezed it, right? This curve is almost, think of it as being elastic. It's made out of rubber. The area under it has to stay constant at 1. So if you squeeze it, pinch it from the sides, then it's going to have to bulge up and get taller because the area has to stay at 1. Same thing as if you pushed down on it, it would flatten out. And so you can kind of think of it that way. And that's what the standard deviation does, is it flattens it out or it squishes it together, depending on if it has a big standard deviation or a small standard deviation. So we need to figure out how to get this area of 1. So you can do a z-score. Your z-score equals a measurement, equals a measurement minus the mean divided by the standard deviation. And we need to find the z-score that corresponds to an area of 1 and then kind of work backwards from there.
Thank you.
So it's going to take a slight, multi-step process. I'll set it up for you guys. So we know we're looking for our X is 150, our mean is 160, but because we're asking for sample size, our standard deviation isn't just 20, it's 20 divided by the square root of n. And that's basically what our z-scores would always be, you know, for this context. This looks terrible. 160. There we go. And so, okay, so now what we can do is we can go to SAS and we can use our quantile function, just like we could actually use tables, right? And we could go, all right, I want to find the z-score that corresponds to an area of 1% below it. And z-scores, remember, come from normal curves that have been standardized. And when they're standardized, the mean is 0 and the standard deviation is 1. So this is the same thing you would get if you just looked up in a z-score table and said, okay, what's the z-score that corresponds to 1%? If you look that up in a table, it will give you this answer, negative 2.32. Now it'll round, it'll probably just say negative 2.33 or something like that. But that's basically the z-score that goes with a 1% area under the standard normal curve. So that's what we would put into this formula. Put negative 2.326. Let's say if we round it to 3 decimals. So now, because remember, z-scores are the same. It doesn't matter if it doesn't matter what our standard deviation is. A z-score still represents the same thing. It's basically saying we're finding a measurement that is 2.326 standard deviations below the mean. Now, if we're on the blue curve, that standard deviation is a distance of 20. If we're on the black curve, then that standard deviation is a distance of like 8 point something, because it's 20 divided by the square root of 5, right? But that's irrelevant, because we're looking for a third curve. We're not looking for the black curve or the blue curve. We're looking for, you know, a yellow curve or a red curve. We're looking for one that's even tighter, because the sample size needs to get bigger and bigger, right? For instance, we could go back here and we could play around with this and we could find it by trial and error, more or less, right? If we go to, there we go. So this is a sample size of 5. All right, let's try a sample size of 10 and see what we get. All right, so now we're at almost 6%. All right, how about a sample size of 20? Let's see what that gives us. Well, it shortens up even more. Oh, it's a little over 1%, right? So how about a sample size of 25? Well, hot damn, that's less than 1%, right? So we know it's somewhere between 20 and 25. Well, we can calculate it precisely using this. Do just a little simple algebra, bring the n over, right? Divide by this, square both sides, blah, blah, blah. Just do some simple math and you'll get an n. Just realize that whatever you get for n, you always have to round up. Even if you got, let's say, 22.1, you would round that up to 23. Because getting 22.1 says, if you had a sample size of 22.1, then the chances of the average of all of those numbers being less than 150 would be exactly 1%, because this is the z-score that corresponds to having exactly 1% of the area below it. But we can't sample 22.1 people. And if we sample less, if we only sample 22%, remember, as the sample size gets smaller, the distribution gets wider. And so if it got wider, then we would have a little bit more than 1%. And we don't want that. We want 1% or less. So whatever the number is, we always have to round up to make sure that we have that amount or less, right? So you'll always have less, because the math will never come out that the answer is exactly 23. You're like, holy crap, that's amazing, right? It won't happen. It'll always be something and a decimal. So you'll always round up, which means your answer will always be a little bit less. Okay. That's how to tackle that one. Does that make sense?
So
Yes.
once we find the end, what do we do with it? Like,
Nothing. You're done. The N is what you're looking for. You're looking for the sample size. All you
oh,
have to
so
do
we're
with it is
looking for
round
N.
up. Because
Okay, got it.
this N represents sample size, right? And that's what they're asking for. How big, how many times do you have to measure blood pressure during the day to basically ensure that the average of all those measurements will be accurate to within 1%, i.e. that they will not be less than 150 more than 1% of the time. So basically you're 99% confident that the average you get is close enough to the mean of 160 that you're not going to get this false reading of, hey, your blood pressure is fine, right? That it's not going to be less than 150, that it's at least going to come back greater than 150 so that you'll tell the patient, all right, you've got high blood pressure, let's start putting you on statins and then other things. And this is all you're doing with this, is you're finding the sample size this way.
Thank you.
Yep. What else?
Dr.
Okay.
McBride?
Yes.
I'm sorry, go ahead. Somebody
No,
else.
you go ahead. You go ahead.
No, go ahead. Finish asking your question. I'll go after you. I don't mind.
Well, I was the one who asked the first question, so you can go ahead.
I was gonna say for 4.70, I think I did something wrong, like with letter C. Like I messed up somewhere and trying to figure out it's C and D that I was thrown off on, like the less than and the between 450 and the 460.
Yeah.
I mean, or 450 and 600. Like I did something wrong, so I just asked for help.
Draw pictures. Just draw a simple picture each time to help you figure out what's going on, right? So we have the mean is here at 513. C wants us to calculate the likelihood of being less than 450. So right off the bat, from drawing a picture, we know that the answer has to be at least less than 50%, right? Because with the mean sits right in the middle, and that means there's 50% on each side of it. And 450 is obviously less than 513, and we're looking for things less than that. So we know this area has to be less than 50%, which is good to know, because when we run something in technology and we get an answer that's bigger than 50%, we can go, oh, well, crap, I must have done something wrong, because I know it has to be less than 50%. Okay, so we've drawn a picture. We know what we're supposed to get, or at least it's supposed to be less than 50%. We're looking for area below something, which is exactly what the CDF gives us. So we don't have to do any kind of manipulations of our answer. Just what we get is what we need. So all we have to do is fill in the bits and pieces. Our point of interest, right? Our X value is 450.
Mm-hmm.
Our mean, 513. And our standard deviation is 130, and we're not making any adjustments because we're just choosing one thing.
Okay.
And technically, you're always dividing by the square root of your sample size. We're in this case, we're dividing by the square root of 1. Well, the square root of 1 is 1, and when you divide by 1, nothing happens, right? So that central limit theorem formula is actually technically always in effect. It's just whenever we only choose one thing, it's like, why bother doing all this extra math that just all equals 1, right? We'll just ignore it at that point. So if we run this should give us less than 450, 31, a little bit more than 31%. Now, if you want in between, that's where you have to do things twice and take their difference, because graphically, that's 450. Now, if you think about a mirror curve, right? Let's assume these two have the same shape because I'm a shitty drawer.
Mhm.
And then, well, you didn't have to agree that I'm a crappy drawer. That's just mean.
I was agreeing with your curve.
And if we take less than 600, it's all of this, right? And you can see that if you take this one and superimpose it on top of it and basically take away all of this, this piece, you're left with the in-between. So we just have to do a CDF of 600 and subtract the CDF of 450, and that'll give us the in-between.
Oh.
And that's the beauty of drawing a picture, is it really helps your mind kind of see what's happening.
Can I ask a question on D?
Sure.
Okay, so in my head, I keep feeling like if it's greater than, if the number is greater than, I need to subtract from 1.
Yes, that is correct.
But I'm talking about when I'm doing the between ones too. So I know we do it when it's by itself, but like when we doing the between ones, I still be trying to subtract from 1. And I feel like you said we don't do that.
No, between you subtract from each other, not from 1.
But you don't do that first, like if it's greater than, like A, on A, I would subtract that percentage from 1.
Yes.
On A of the same question, how I would subtract that from 1.
Yes.
I keep trying to do the same thing for the between ones.
Okay.
On the between ones, we don't do that, correct?
No, because the reason
got
why
it.
you subtract from 1 on greater thans is because the CDF gives you everything below it. If you need everything above it, that's why you subtract from 1, because the total area equals 1. So if you subtract this piece, it will give from 1, it will give you the other piece. That's not what between is asking for, right? Between is asking for the between. It's asking for this stuff here. If you took the CDF of 600 and subtracted that from 1, that would give you this piece over here. That's not what you want. So that's why you don't subtract from 1 when you're doing an in-between. Now you could subtract from 1 and then do some more math to get the answer that you want, because I mean, let's look at this, right? If let's say there's, just make the math easy. Let's say there's 20% here, okay? Let's say you run the CDF of 600 and it gives you 90%. Well, you subtract that from 1, that tells you there's 10% over here. Does everybody follow my math so far? My fictitious math, right? So if we know there's 20% here, and we know there's 10% here because we did the CDF minus 1, then how do we find the area of the blue stuff?
Make it add up to 100.
Right,
Yeah.
exactly. We know that these 3 pieces have to make 100. So you take 20 and 10 away from 100, and that tells you there's 70% left in the middle. So you could do the whole subtracting from 1 thing and still get the correct answer. You just have to draw a picture, see what subtracting from 1 is really giving you, and then realize you have to still do a little math to figure out the leftover bit. It's a little faster, a little leaner, and a little more efficient to, instead of subtract from 1 and do all this, you just draw the picture and realize that if I do a CDF of 600, it gives me all of the green stuff. If I do a CDF of 450, it gives me the black stuff. If I want just the blue stuff in between, well, if I look at the picture, that's just the green stuff. If I chop off the black stuff, right? If I subtract the black stuff away from it. So the green stuff is the CDF of 600. The black stuff is the CDF of 450. So I take the green stuff and subtract the black stuff from it, i.e. I take the CDF of 600, subtract the CDF of 450 from it, and that gives me the bit in between. So that's why you're not subtracting from 1, you're subtracting one of the CDFs from the other CDF to get the in between the fastest and easiest, most efficient way. But you could do it the other way if that, you know, just fits in your brain better. That's fine.
Okay, so let's say for instance, I wanted, so you see how it says between 450 and 600. If I wanted to use the 600 that I got from A, but I still wouldn't be able to.
Well,
600.
yes, you can use
What-
the 600 you got from A, because if you ran it in SAS, you would have got an answer for 600, and then you would have subtracted that from 1 to get the actual answer for part A. But the number that you subtracted from 1, you could still use that in part D. Yes.
Okay, got it. Thank you.
Yeah. All right, what else? Any other homework questions?
Oh, sorry, Brady, you go. You were.
I'm sorry. The only thing I was gonna say, we have until tomorrow morning to send you the homework again, right? To look at it.
Yes.
Because I never send it. So I think I'm actually gonna send it this time because I think that
Yes, yes. Just get it to me no later than, I think I said 6 a.m. Pacific time, which is 9 a.m. Eastern time.
okay, thank you.
Yep. Amy?
Yeah, I just had a quick question about the final project.
Yes.
Part 2 is making me nervous because it felt too easy and it felt tricky. So we've got the Excel sheets and we've got
I'm
the,
glad you brought this up because part 2
Okay.
is mind-numbingly easy.
okay, I just wanted to make sure, because I was like, there's got to be something more to this. Okay,
Nope.
thank you.
No, it's silly easy. It's ridiculously easy. Yeah. Don't overthink it. You're literally just calculating some simple conditional probabilities, and then you're ranking the judges based on what you feel is the most important thing. So one last, before we get into this, any other homework questions? Then I'm going to dive into the project and do that for the rest of the time.
For 488, would you suggest doing that in StatCrunch? I watched your videos and I confuse myself more than anything watching 2 different class videos, and now I don't even know how to do it.
So in 88, compute the exact probabilities. Yeah, so 88, obviously you would do a binomial, and then you would do the normal approximation using less than 5, meaning 4, right? And then for part B, you go, okay, well, I know that I can improve the results by, instead of using 4 on the normal approximation, I can use 4.5, because as we talked about this last week, if we're trying to fit a normal curve to this discrete binomial distribution, each one of the bars of area that sits above those discrete numbers is centered on that discrete number. So the bar that represents the probability of 4 is centered on 4. And if we want to capture all of that area, then we need to make sure that we come all the way up to 4.5, because that would be the upper edge of 4. And then we would get everything below 4.5, and that would give us a more appropriate approximation for the binomial. And all of that, yes, can be done in SAS, right? Because you're running either the normal CDF for the approximation, or you're doing the binomial CDF right here for the exact values. And yes, it could be done in StatCrunch, but just ignore the StatCrunch thing unless you have StatCrunch, then great. But yeah.
Well, I have StatCrunch. It just seemed easier in StatCrunch.
Oh God, yes. StatCrunch.
Okay,
is
I just
many
wanted to,
times
that's
easier.
okay if I do in that, right? I teach, so I actually have access to it.
Oh yeah, absolutely. Yeah.
Okay, cool. I just wasn't sure if I was allowed to use that or not, if that was an example, if I could for this.
No, yeah. I talked about this at the beginning of the class. You know, we used to have to do everything in SAS, but since the university says you can use any technology you want, I'm fine with StatCrunch. I love StatCrunch. I use it in all of my classes because it is such an easy tool to use.
I felt like I was cheating, so I just wanted to make sure.
No, you're fine. I will tell you, however, that your 810 instructor might not let you use it. they shouldn't have a problem with it because of the school policies. But I would be more concerned with your dissertation committee not letting you use it. Just be aware.
Okay, thank you.
Yeah.
So
All right,
I
and-
have a question about that. On one of your videos for A, you used 5. So you broke down the standard deviation because you said that it didn't look right for whatever that they gave us. So then you broke it down and it became 2.23607.
Yeah, that
But
was
then
the
you
Z-score.
still, right. So then you still use 5 as the X for that, for A.
No, this number, the Z-score, came from finding 1% of the area.
I'm on 4.88 on A.
Okay.
This one here. Oh, okay. No,
Yes.
you could do the normal you can do the normal approximation with either 5 or 4. You could make an argument for either one. I would probably start with 4. So if I did it with 5 in my video, that's probably a mistake from earlier. I mean, you could, because you're doing a normal approximation, a lot of people would just use the same X, right? They would just use X equals 5. But in a binomial sense, right? If we're talking about a binomial distribution, which is discrete numbers, if you want to find the probability of being less than 5, then what's the largest number you're actually going to include?
So it'll be 4.
Right. So that's why you could also argue that the normal approximation would make sense to let X equal 4, because we know that's the largest number that we're going to include in the binomial. But either of those, letting X equal 5 or X equals 4, is going to give you a pretty crappy approximation. If you run them both, you'll see the numbers are quite different. But if you then adjust it to 4.5, you get a pretty damn good approximation. So that's basically what we're trying to learn here. 8.8 is really just trying to point out the fact that you kind of need to do that continuity correction if you ever want to approximate the binomial with the normal, which you would never do in real life anyways.
So when it says compare your results, we just comparing A and B.
Yes, yeah, you're comparing the crappy approximation you got in A to the better approximation you got in B. Okay, anything else? All right, so data sets. So part A of the project is pretty straightforward. It's pretty easy. There's one question in part A that's going to trip you guys up. And it's the one that asks about the probability that this new data that they found came from the same ship. I think it's question 4. Go back and watch a bunch of my week 5 videos. I've gone over it a million times. And it basically, it's a multi-step process. It's not that difficult. It's just the setup that is tricky. For part 2, it's actually really simple. And again, if you watch any of my videos, I've done this a million times as well. It's super easy, especially in Excel, because you can write a very simple formula in Excel and then drag to populate all of the other cells. So this column here, right, is probability of an appeal. Now remember, probability is just good over total. So the probability of an appeal for this judge is simply just the number of appeals divided by the total number of cases they saw. So we can literally just say, hey, this is going to equal this number divided by this number, and that's my probability of an appeal. Now I can leave it as decimal, or I can change it into a percentage. Just if you're going to change it into a percentage, please be more accurate than a whole number. Give yourself at least 2 decimal places, right? And then if I grab this and drag it, it automatically does it for all the rest. Pretty slick, right? Then probability of a reversal. Well, isn't that just going to be reversals divided by cases? Yep, easy. Do the same thing. Okay, how about conditional probability of a reversal given an appeal? Remember, given just means that becomes our new total. So instead of a probability of just a reversal in general being number of reversals divided by total cases, the probability of a reversal given an appeal means number of reversals divided by number of appeals. So that's how you do that one. It's just going to be equals this divided by this. Again, I'm going to change it to this, give myself 2 decimal places, drag it right, and do all the rest. Simple and easy. Well, so now you've got these 3 things. I'll do this real quick as well. It's going to be reverses divided by this, do this, 1, 2, zippity, right? So now you're going to have all these percentages, and they say, okay, now rank your judge. Well, this is where you can choose how to rank your judge. You just need to justify your decision. This is what you would quote unquote discuss, right? Because all 3 of these measurements could be easily argued as a good measurement tool. You could say, all right, well, I'm going to rank my judges by whoever had the lowest percentage of appeals, right? Because if the judge is doing their job and they're doing everything correctly, then there shouldn't be grounds for appeal. So they should have less cases appealed. And so whoever had the smallest percentage, right? So I'm basically going to take everything and sort it by this column, right? I can go, okay, I'm going to take everything and I'm going to go data, sort, and say it's got headers. So I'm going to sort by probability of appeal, smallest to largest. And then now I know that this is going to be judge 1, judge 2, judge 3, right? And I can drag this and rank them all as well, because I think the probability of an appeal is the most, important aspect of a judge. And that's how I'm going to rank my judge. But you could go, no. Things get appealed all the time for stupid reasons. And then they get, even though they appeal it, it doesn't get overturned. So I think it's more important that we do it on reversals. So I'm going to instead sort it by reversals, smallest to biggest, and I'm going to rank my judges that way. And you're going to say, no, that's still not good. I'd rather say that it's just how many of their appeals, what's the probability of an appeal being reversed, and I'm going to sort it by this, and I'm going to rank them based on that. That's basically all you're doing, because those are the only 3 options. So those are the only 3 arguments you can make. And you're just doing it for all 3 courts. Don't forget, folks, that you also have to do the totals, right? So when you're dragging and getting these computations, you also have to report the totals for the court, right? So what's the probability of just any court case being appealed in the domestic relations court? And what's the probability of any court case in the domestic relations court being reversed, right? So you have to fill in those boxes as well for all of them. And then this merge data set, all I did was I put all the judges together in one set, so I could then rank them all together rather than individually. That's part 2. That's all there is to it. That's all you're doing. It's that simple. It's really, really easy.
Thank you, because
Yep.
that's what I did, and I was like, it can't be that simple.
Yeah, it is. It really is. Okay, so any other questions on part 2?
I do. So do we just, for basically for number 1, the probability of cases being appealed for each judge, do we just copy and paste that whole line?
The best thing to do would be to just copy and paste your whole table just once for everything.
Oh, okay.
You can just say, for this question, see this column, see the table, see the table, see the table.
Okay, got it.
Yeah, that's fine.
Dr. McBride, when I was ranking though, there were some probabilities that were the same. So I ranked 2 of them the same.
That's fine.
And then skipped a number and went to the next.
That's totally
okay.
fine. That's absolutely fine. Yep, absolutely. You could also, instead of doing that, if they were the same, you could then use one of the other probabilities as a tiebreaker.
Well, that's a good idea. Thank you.
Yeah. And there's actually a way to do that very easily in Excel, right? Because you can sort and then you can add a level. So first it's going to sort by probability of appeal, and then it's going to secondary sort by reversal. So if there is a tie, then it would list them in the order of this second one being smallest to largest, and then everything's done for you, and then you can just do the numbers really quick. Okay, anything else about part 2? Okay. Part 1, make sure you pay attention to the questions. A lot of students just don't answer everything because they, I don't know, missed it or something. Right? You have this final project paper here that it walks you through everything you're supposed to do, right? Describe each probability distribution in the given Excel file. Use histograms and numerical summaries such as means and standard deviation and their interpretations in your explanations. You're supposed to do that for every single one of the probability distributions in the Excel file. I think there's 4 or 5 of them, right? So you should have a histogram and summary statistics for all of them.
So in one of your videos, you said the histogram was ugly. So then you said you used the bar graph.
Yeah. Either one's fine.
Okay.
This is the one that I said is tricky, number 4. So make sure you think about this, right? The first thing you need to do is find the probability of at least 5 or 6 immigrants, right? And that just comes from your probability distributions for that question. So you just add those 2 together and that gives you a probability. And then you're just doing basically a simple binomial distribution on the likelihood of getting more than 4 successes given the probability you got from that bit with a sample size of 6. And that's how you run it. It's pretty simple. It's just figuring out that first setup is the difficult part. Yes.
Yes, Dr. McBride. I had a question on the question 2. Is it that simple? Is it just basically taking the cost and then multiplying it by the value that you get from the table?
Well, you don't have, not the value you get from the table, the value you get from your summary statistics here.
And that's just for one of them, right? You're not expecting us to do, it's not asking us for us to calculate 3.
No, because they're only doing the average cost based on the mean of the number of freights. So you only need to use the average number of freights that you get from that distribution times the average cost, or
Gotcha.
get the overall average cost. Yeah.
Okay.
Or times the cost of a freight, sorry, to get the
Times the
average
cost,
cost. Yeah.
okay.
Yeah, you're just using that one. And guys, there is a very specific way of getting means and standard deviations for probability distributions in SAS. You have to make sure that you're using a weighting variable. So just make sure that you're doing it correctly to get the right answer. And again, I go through it in a bunch of other videos. So just go back and look through those videos and you'll find me walking through it to show you how to do it. Let's see what else. The last thing is part 3. Everything in part 3 is completely made up. It's all a thought experiment. You do not have to have real data. You do not have to gather real data. You don't have to analyze real data. None of that stuff. Even in this part 6 where it talks about calculating probabilities, you're basically calculating probabilities with just made up things. So don't worry about having real data. Now, if you have real data because you've already done some research, great, use it. But if you don't, that's fine. What I would really like you guys to do in order for this assignment to actually mean something to you is to try and answer questions 1 through 5 in the context of your dissertation, what you want to do your research on. So describe the problem that you're trying to research. Describe, what you think the solution is, because I mean, all of your dissertations should basically be of the form, here's something that doesn't work well. Here's how I think I can fix it. Here's, how I'm going to gather data to see if my fix is effective or not. Here's how I'm going to analyze that data. Here's the results of my data. And this tells me whether or not I fixed the problem. That's basically what every good dissertation should be, because otherwise it falls in the category of so what, who cares, right? Unless you're trying to fix a problem, why the hell should I spend the time reading your paper? So that's really, in general, what every good dissertation should be is, here's something that doesn't work. Here's a problem that exists. Here's a possible solution to that problem. Here's how I'm going to go about investigating that solution. And then here's how I'm going to actually gather some statistics so I can actually quantifiably measure whether or not this solution works. And so try to do this in the context of your dissertation. Now, if you're not far enough along to even have a clue as to what your dissertation is going to be about, then you're going to make everything up, right? Just pick a topic, pick a problem that you think is an important problem, whether it has anything to do with your dissertation or not. Heck, you want to, gerrymandering is a problem, for voting rights. Okay, so here's a solution I think could solve it. Okay, then what kind of data would I have to gather to test that solution? And then how would I analyze that data, right? It's that kind of thing. So that's how you would treat 1 through 5. 6 is, it'd be nice if you could do 6 in the context of your actual research question that you describe in 1 through 5, but you don't have to, because 1 through 5, your research question might not include continuous data. If it does include continuous data, something that's been measured, not counted, then by all means, use the context and the question and the variables and the data, that you'd be gathering in your scenario. Use that to come up with this fictional stuff. If yours isn't going to have continuous data, then again, just create a whole nother scenario that has a continuous variable associated with it, and then do question 6 in the context of that question. Because literally, guys, all this stupid question is the homework questions that we're doing this week over again, but with your scenario instead of the scenario in the homework. And I'm going to show you what I mean. I'll put them side by side. And I apologize, I know side by side makes things small, but I really want to point out how they're exactly the same. All right, so this first question, I know it's impossible to read now, so I'll read it to you. It says, the probability that the continuous random variable is greater than a specific value. That sounds an awful lot like the probability that y is greater than 250, or the probability that y is greater than 150, right? It's the same damn question, only now the quote unquote continuous random variable is yours instead of this generic random variable, or the one that we saw about this generic, well, it's not generic, this college board tests, right? That's the random variable here. So you're doing the same thing, you're giving it a whole new context. And the specific value, the greater than a specific value, that's you. You can pick that. Your specific value can be 250. Your specific value can be 25. Your specific value can be anything, right? So the less than, just like this question, less than 450. The probability that the continuous random variable is between two values. Between two values. That sounds an awful lot like this question, or an awful lot like this question, right? So you're just doing the same stupid stuff we're doing in the homework, You're just now doing it under the guise of your research, right? Ultimately, that's what 6 was supposed to be, is it was supposed to be in the relationship to your research. So hopefully you had a question where there was a certain number that meant something, like you were gathering data and a score above 120 meant something. So then obviously 120 would be your, your X value. And when you did greater than, you would go, okay, what's the probability that my data is going to be greater than 120? Because 120 means something in the context of this research. Well, that's almost never going to happen for any of you. So I've been arguing for a very long time, this is a stupid question. They should get rid of it because it's a waste of time for a lot of people, because it's the same damn thing as the homework, and it doesn't matter because the context doesn't fit. But I don't make the rules. So it's probably not going to make any, sense to you. That's why, because this whole thing is going to be completely made up. So what the hell are you learning from it? Not much. You've already done this. It's just an opportunity for you to generalize these questions, and hopefully from that understand the concepts and the algorithm, right? The recipe for getting these answers in SAS and stuff, to put a little bit more to it, so you don't just get an answer out of SAS and go, oh, here's the answer. You actually kind of understand a little bit more about what it means. So the percentiles question, that's just, this, the 90th percentile, this one, or even the one that asked us to, be at most 1%. Sure, that was asking about the sample size to get to the 1%, but when we calculated the 1% z-score, that was the same thing as finding a percentile, right? And then graphs to visualize your solution. Well, that's basically these pictures that I keep drawing, right? Is doing those. Now, if you have access to StatCrunch, then you can get some beautiful, easy, awesome normal distributions that are shaded and everything out of StatCrunch. Really cool. If you don't have it, well, then find a tool online that'll create normal graphs for you, or draw them by hand and snap a picture with your phone and slap it into the Word document that way, right? There's loads of ways you can get something like this into your paper. And that's it, guys. The whole explaining your thinking behind your choices of using formulas, tables, blah, blah, and then discussing the results. That's just, you're kind of discussing it as you go through, 1 through 5, especially. You can explain 6 a little bit, but there's really not a lot of explaining to be doing, because you're creating everything yourself, right? You come up with the continuous variable, you come up with the X specific value. So what are you going to explain? I mean, if it has a real context, then you could explain why you chose that X value, because it had some sort of importance to it. Or if you create a scenario, then you could discuss, in this fictitious scenario, why you chose the values that you chose. But I wouldn't waste a lot of time on that. I would only spend time on if it has to do with your dissertation. Yes, Latanya.
So listening to you say we don't have to spend a lot of time on some things, and we've already demonstrated, or hopefully demonstrated, that we know the answer or information in the homework assignment that's also due. How much of an answer do you want for, each question listed, like a sentence or two, or do you want like a whole?
Are you talking about the 1 through 5 part here in part 3?
Yeah, and even, with answering some of the questions in part 6, I know you said there's diagrams and stuff like that, but how detailed do you want the information?
Well, I would say that part 6, you don't have to describe much at all. Parts 1 through 5, you're going to need to describe a little bit more. I'm obviously not looking for something that's dissertation level descriptions, but I mean, if you're going to describe the setting of your problem, I'm thinking that's probably going to take at least a few sentences, if not a paragraph or two. If you're going to define exactly what you want to solve in this scenario and your solution plan, again, that's going to take probably a paragraph, maybe 2. Describe the type of data you collected. Well, that's going to be shorter. That's probably only going to take a couple sentences. Describe the possible variables. Again, only a sentence or 2, and say, okay, it's this variable. It's a qualitative variable, blah, blah, blah. This variable is a quantitative variable, and it's continuous or it's discrete, that kind of thing. So that's gonna be pretty quick. And then describing the statistical methods. for analyzing the data. Again, that's not going to take a lot. You know, I'm going to run some summary statistics on it and look at the averages, blah, blah, blah. I'm going to maybe create some pie charts or bar graphs, or, you know, whatever seems to be appropriate for the kind of data you have. And then providing evidence that this data follows a normal distribution. I would ignore that unless you have real data, which none of you have. So, you know, again, if I created this, there would be a lot of changes because you can't really provide evidence that something. So maybe discuss how you could provide evidence would be a better way that this should be, you know, because it would be nice if you guys remember the techniques that we could use to determine if something has a normal distribution or not. We've done it twice in this course on 2 different assignments. So it'd be nice to see that you remember that. So instead of providing evidence, I think it'd be nicer if you could just describe quickly, easily in a sentence or so of what method you would use to determine if your data follows a normal distribution or not.
Okay, the reason why I was asking also about number 6, because in the top of the, like right next to number 6, it says provide a detailed step-by-step explanation.
Yeah.
So
Yeah.
you're saying we don't need to provide a detailed step-by-step explanation for number 6?
No, because I mean, what are you going to say? I put the numbers in SAS and hit run.
Okay, I'm okay with that. I just want to make sure when
Yeah, no, I'm
that.
glad you asked, Latanya, because a lot of these directions, I honestly don't understand them. I don't understand what they're trying. I'm an educator and I always look at a question and go, what would the student learn from this? And for the life of me, I cannot figure out what they're trying to get students to learn from this. So yeah, don't worry about a detailed step-by-step. Just describe what the variable is. You know, your made up random variable. I want you to prove to me that you know what a continuous random variable is. So describe what it is that you're quote unquote measuring that's giving you this continuous random variable. And then set up the scenario of, well, I want to know the probability that it's less than blank. And here's a picture that shows what that would look like. And then here's my result, right? Because you're gonna create the random variable, but you're also gonna basically say, and I am God, and I say that this random variable has a mean of 120 and a standard deviation of 7. So be it, right? And then based on that, here's the probability of something being greater than 150, right? Here's the probability of something being less than 107. Here's the probability of something being between 100 and 110. And, you know, here's the 25th percentile of my data. Here's the 90th percentile of my data, you know, that kind of thing. And then here are all the graphs that represent all of these. So when I do greater than something, here's a little graph that shows it. When I do less than, here's a little graph. When I do in between, here's a little graph. All of that is just a way of you proving that you know how to get these answers out of technology, which is a good thing. And it proves that you know what a continuous random variable is, which is a good thing. And that's really the only kind of assessment kind of things that are important to me in question 6. So there really aren't any detailed step-by-step explanations of the solution that I can think of.
Okay, thank you.
Yep. And guys, even though we're not meeting next week, that doesn't mean I'm a ghost in the wind, which I heard the other day, and I thought that was so funny because does the wind really even affect a ghost? But anyhow, if you have questions, email, post them to the doctoral dialogue. I would prefer that you post them to the doctoral dialogue because I get an email saying, hey, somebody posted here. And then I can go in and I can answer it. And then everybody can see both your question and my answer. Rather than your question just being, you know, in a void where nobody else sees it. But if you don't want to post it, you know, because you feel embarrassed or something, by all means, just email me. And I'll answer these things because some of this stuff might still seem confusing or you're not sure how much detail you need to put into it and things like that. Okay, anything else?
One quick question about part 3 on the final. Would would it be good, would it be acceptable, like if we held surveys in other classes where we,
Oh, yeah.
like judged what a
You want to
liking
reuse
scale?
you want to reuse survey data that you got from another class? Is that what you're saying?
Yes, and
Absolutely.
it ranks like with a Likert scale.
Yeah, absolutely. That's fine. Just know that obviously a Likert scale is not continuous, right? So you couldn't use that for part 6, but yes, absolutely. You can reuse that stuff here. I'm not asking you guys to reinvent the wheel.
Okay, thank you.
Yep. Anything else? All right, guys. Sorry for running late. I just want to make sure I answered any questions you had. Like I said, go back and watch the other videos for previous week 5s if you need help with any of the part 1 stuff, because I know I've gone through them all time and time again. And you should be fine, right? Email me or post any questions, and you guys you'll nail it and you'll be done and you'll be on your way to 810. All right. Thanks for showing up.
Bye. Thank you.
Yep. Good night, everyone.
Thank you.
Dr. McBride, just to confirm, we still have till Friday morning, or do you want our stuff by tomorrow morning for this homework?
Oh, you're right. Thank you, because today is Wednesday.
Yeah, when they
Yes.
said that earlier, I thought maybe I had that confused, but I can't find an email saying you need it by tomorrow. So I just want to make sure we still have tomorrow night to finish.
No, thank you.
I am so happy you asked that question, Jessica, because it wasn't just me. I was like, oh crap.
Yeah, I was like, I don't want to pull an all-nighter to do the last 4 if I don't have time.
No, you're right. Yeah, no,
Tired.
Friday morning is the cutoff. I forgot that today. is
Thank you.
Wednesday. Yeah,
Okay.
you're good. Thank you for asking that.
Thanks so much. Have a great night.
Thanks, you too.